So these are pulsed laser sources, whereas the gas laser sources are continuous laser sources. So they are called CW, continuous wave laser radiation. You can write it down that CW means continuous wave laser radiation. Gas lasers produce continuous radiation, also semiconductor lasers, which we shall take up next day. But solid state lasers like ruby or uh, uranium in calcium fluoride or neodymium in YAG, they produce only pulses of radiation. Now, as we noted in connection with ruby laser, uh, generally over the duration during which the exciting radiation is falling on the lasing material, that is over the period of something like 2 to 3 milliseconds, when the xenon flash lamp is uh, producing radiation, several short bursts of radiation are produced by the laser source, that is the ruby crystal. So each short burst or spike has a duration of a few hundred nanoseconds. Then there is a gap of a few microseconds, then another burst, then another gap, then another burst. And the whole thing takes place over the time 2 or 3 milliseconds during which the flash lamp is in operation. So uh, every short burst delivers a small amount of energy. So the entire amount of energy that is radiated by the laser beam is not delivered in one pulse, but over many short pulses. Now, if it could be arranged so that only one pulse is produced, then you can imagine that that pulse will carry a tremendous amount of power. Note that power is energy delivered per second. So if the pulse has a duration of say 1 microsecond and the uh, power is say 1 megawatt, then the actual amount of energy delivered is only 1 joule. 1 megawatt into 1 microsecond is 1 joule. So the amount of energy delivered is not that large. But the amount of energy delivered uh, per second, that is the power during the occurrence of that burst of radiation or spike, is tremendously high. And such ultra short pulses are very useful in many applications. For example, in studying the development of chemical reactions, photochemical reactions, for example, photosynthesis. You flash a burst of radiation on uh, a leaf or say chlorophyll in the presence of water molecules and oxygen and so on, and then you try to find out what happens with the progress of time. So, and many other things. So such small bursts of radiation are very useful from many physics application points of view. Now, how can you produce such a short burst of radiation? For this, you do not allow these multiple bursts to take place. You want to suppress these multiple bursts so that the entire energy accumulated in the atoms of the lasing medium are in the lasing medium is delivered in one pulse. The technique for doing that is known as Q switching. You remember what Q is. Remember the definition of Q, the quality factor. This is equal to omega, the mode frequency, into energy in the mode divided by energy dissipated per second. This is the definition of the Q factor. Q equal to omega, the frequency of oscillation, into energy in the mode of frequency omega divided by energy dissipated per second. When I say energy in the mode, I mean energy in the form of electromagnetic radiation. also you want to know how much energy is in the form of electromagnetic radiation at frequency omega. So the Q switching is like this. When the exciting radiation from the xenon flash lamp is illuminating the ruby rod, you don't want hello, Vaivallo, good morning.
Good morning, sir. Sorry for being late.
Okay, continue. So what happens is that if in normal course of action, as I just mentioned, when this exciting radiation excites some of the atoms to the metastable state of chromium ion, these metastable states decay to the ground state and produce the lasing radiation. So this lasing radiation will cause the by stimulated emission process other atoms to de-excite. You don't want to do that. So therefore you do not allow this lasing radiation to be present in the ruby laser to the extent that it would cause huge amount of stimulated emission. So to prevent the lasing radiation from being present in the lasing material, you have to arrange for Q to be low. Remember again the definition of Q. Q equal to omega into energy in the mode divided by energy dissipated per second. So you have to reduce the energy in that particular mode. That is the amount of energy in the form of lasing radiation. So you keep Q low. If you can keep Q low, it implies that the amount of lasing radiation present in the ruby rod is low. Then there is very few stimulated emissions, and the exciting radiation from xenon flash lamp keeps increasing the population of chromium ions in the metastable state. It grows and grows and grows. And the population difference between the metastable state, or what we refer to as state number 2, and the ground state, that is state number 1, becomes very large. It becomes very large. Okay? And then you suddenly allow this at that stage the value of Q is low because the energy present in the form of electromagnetic radiation in the lasing medium is low, so Q is low. But then you suddenly allow, by a special technique or trick, the stimulating radiation to grow in the lasing medium, and as it grows in the lasing medium, it causes further growth because there are a huge number of atoms in the metastable state ready to de-excite. So a huge amount of energy appears in the form of electromagnetic radiation within the cavity, and which is then radiated away as a burst of radiation. So that way you get a huge output pulse. So see, initially Q was low because the amount of energy present in the mode was low, but then at the last moment you allow the amount of energy in the form of electromagnetic radiation to grow to a very high value, so Q then becomes large. And so this technique makes Q go from low value to a high value. That is referred to as Q switching. Initially Q is low, and just before the pulse is emitted, the Q goes high. That is Q switching. Now, how do you achieve Q switching? There are various techniques. The earliest technique used a mechanical arrangement. That mechanical arrangement is shown in figure 11.1. I'm afraid that when I photocopied that page, you can go to the next page. Yes. Yeah, okay. Right. Yeah. So you can see this page here in figure 11.1. You see an arrangement. The rod in the center is the ruby rod, and there are two mirrors on two sides. One of the mirrors can be rotated about an axis. This is the mirror that has 100% reflectivity. That is, the reflection coefficient is 1. When these two mirrors are parallel to each other, then light can go back and forth between the two mirrors and thereby cause the excited atoms in this metastable state to de-excite. But if the mirrors are not parallel, then when light falls on the 100% reflecting mirror, it gets reflected in a direction different from the direction of the axis of the ruby rod, and therefore it gets lost. So what is done is that the flash lamp is turned on, and at the same time the rotatable mirror is given a rotational motion so that the parallelism is lost. The mirror rotates, and because light is not reflected back into the ruby rod, the radiation density does not increase within the ruby rod. So the mirror rotates, and because the radiation density is low, few number of excited chromium atoms can decay to the ground state. So the population of chromium atoms in the metastable state grows and grows. Then after one rotation, the rotatable mirror becomes aligned with the fixed mirror, and at that instant or over a short period of time around that instant, radiation can go back and forth between the two mirrors, and by that they can cause de-excitation from metastable state, and suddenly the number of photons within the ruby rod increases to a very high value. And then this is emitted as a burst of radiation to the fixed mirror, which has, say, 95% reflectivity. That is the right-hand side mirror. So this is the mechanical process. So the rotation rate has to be very high. As you see mentioned in the text, it is something like 30,000 rotations per minute. That is 30,000 RPM, or 500 per second. That means the rotation period is something like 2 milliseconds or 1 millisecond. So that coincides with the so arranged that this period agrees with the time period during which the flash takes place. As I mentioned, the xenon flash lamp emits flashes of duration something like 2 milliseconds, and the rotating mirror has a period of rotation which is also equal to 2 milliseconds. So when the flash just gets over, the rotating mirror again gets aligned with the fixed mirror, and then this sudden burst of radiation is delivered by the phasing rod. So this is the mechanical arrangement. But mechanical arrangements are very clumsy, because you have to have motor and all those mechanical parts. So they are not very reliable. The timing may be not so accurately ensured. That is why you choose electro-optic arrangements. Okay. The first electro-optic arrangement that we discuss is the arrangement that uses a Kerr cell. So if you can scroll down slightly, so then, yes. The figure also, yes, just a little more. Yeah, that's it. So here is shown the arrangement using the Kerr cell. Now this diagram is not very illuminating. That is why I have sent you a hand-drawn diagram. If you can, first let us see this diagram. You see, there is the active material, which is the lasing medium or the ruby rod. Then you have on the left-hand side a 100% reflecting mirror, and On the right hand side, just near the ruby rod, there is a polarizer. The polarizer is followed by a nitrobenzene cell, which is the car cell, and then you have a mirror which is say 95% reflecting. So that is the output mirror. Now what happens is that when the flash lamp is started, the ruby rod emits radiation. So part of it goes towards the fixed mirror, the 100% reflecting mirror in the left hand side gets reflected, and some of this goes in the to the right anyhow. So this radiation passes through the polarizer. As it passes through the polarizer, it gets polarized in the direction of the pass axis of the polarizer. Then it falls on the nitrobenzene cell. This is the car cell. Now if you can just for a moment, Surendra, show the hand-drawn diagram of the car cell. I sent it to you maybe yesterday. Yes, here it is. So actually the way this cell is oriented is like shown. You see, it's rotated by 45 degrees with respect to the vertical direction. The cell is like a cube within which you have this nitrobenzene liquid, and the cube is so rotated that its edges make 45 degrees with the vertical direction. Now the polarizer produces radiation which is polarized in the vertical direction. So this polarized radiation makes an angle of 45 degrees with both sides of the entry phase of the cell. The entry phase is a square, which is you can say it is the XY plane, and the direction of propagation is in the Z direction, say, and so this XY plane is actually a square which is rotated by 45 degrees with respect to the vertical direction. So because the incident radiation from the polarizer is polarized in the vertical direction, so both edges of the entry phase make angle of 45 degrees with the vertical direction. Now, as I have shown in the diagram, two of these faces, say faces parallel to the faces which are shaded, that means there is a layer of metal on those faces. These faces are essentially say perpendicular to the x direction, that is, these are YZ faces. So on these YZ faces are attached two electrodes, and via these electrodes voltage is applied between these two faces. So the voltage is assumed to be V. So when you apply a voltage along between those two shaded plates, there's an electric field in the direction that is perpendicular to the plate, so it is in the x direction, let's say. The electric field is in the x direction. And when that field is present within the cell, the nitrobenzene acts as a uniaxial crystal, like say calcite that you use in nickel prism. Calcite is an uniaxial crystal. Similarly, quartz is an uniaxial crystal. So when you apply an electric field in the stated direction, the nitrobenzene within the cell acts as a uniaxial crystal with the optic axis along the direction of the electric field. Now, what happens is that the radiation that enters the cell has an electric field which is perpendicular to the which is in the vertical direction, and so the electric field can be split up into X and Y components. X component along the direction of the electric field and Y component perpendicular to that. Now, because the cell has now become an uniaxial crystal, uh, the it behaves as a birefringent material. That means it is a double refracting property. And as in the case of calcite, the uh, the refractive index along the optic axis, that is the direction of the electric field, and the refractive index perpendicular to that direction, in our statements, these are the X and Y directions, they become different. Mu along X direction, that is along the electric field, and mu perpendicular to the X direction, that is Y direction, are different. And therefore, when you split the electric field into these two components, Ex and Ey, which are by the way equal because the angle that the electric field makes with the X and Y axis are equal to 45 degrees. So the two components are equal in magnitude. These two components propagate with different velocities because the refractive index is different along the X direction and Y direction. So they gradually develop a phase difference between themselves. And when this radiation comes out of the other phase of the crystal on the right hand side, a phase difference is produced between these two components, which depends on the length of the cell along the Z direction, that is the direction of propagation. The more the length, the more the phase difference will be. And so, if you can arrange the size of, if you choose the cell in such a way that the length of the cell is just right to produce a phase difference of pi between the two components, then what happens is that the cell acts as a half-wave plate. So, what is a half-wave plate? A half-wave plate is a, say, quartz plate which produces a phase difference between the two polarized components of the incident electromagnetic field. The two polarized components propagate at different velocities, and when they come out, the phase difference between them differs by pi. Initially, they were in phase, but when they come out of the end phase, they have a phase difference of pi. As a result, what happens is that the radiation that comes out of the cell is now again plane polarized, but the plane of polarization is perpendicular to the initial plane of polarization. In other words, since the initial plane of polarization was assumed to be vertical, the radiation which comes out of the cell has a polarization which is horizontal. This is the characteristic of a half-wave plate, and you make the length of the crystal such that it has that same characteristic as the half-wave plate. But remember that a half-wave plate always produces this rotation of plane of polarization by 90 degrees, whereas a car cell does it only when an appropriate electric field is present. In the absence of the field, the nitrobenzene liquid acts as an isotropic liquid, isotropic homogeneous liquid, and no phase difference is produced. So you can produce a phase difference, or you may not produce a phase difference. You can produce a phase difference which is equal to pi, or you can produce any other phase difference by changing the magnitude of the electric field and the length of the cell. That is the kind of liberty or freedom that you have. So this radiation in the car cell, I was just going to the focal cell. Yeah, in the car cell, the phase difference that is produced is equal to pi by 2. The length of the cell is so chosen that the phase difference produced is pi by 2, so it acts as a quarter wave plate. Okay, a quarter wave plate, which is half in thickness, in comparison with a half wave plate, produces a phase difference of pi by 2 between the two components. And when a phase difference of pi by 2 is produced, then the uh, radiation that comes out of the uh, end phase is circularly polarized in this case, because the two components Ex and Ey were originally equal in magnitude. So the output from the nitrobenzene cell is circularly polarized, because a phase difference of pi by 2 has been produced. One component has gone ahead of the other component by an angle of 90 degrees. So if you just consider two simple harmonic motions which were initially in phase, but now one has advanced in phase by pi by 2, you can easily see that when you combine these two simple harmonic motions, you find a circularly rotating displacement vector, in this case an electric field. So the electric field rotates along a circle. If you, at a particular place, you will find that the electric field is rotating in a circle, and you say that it is circularly polarized. So this circularly polarized light then falls on the right hand mirror, gets reflected from that as circularly polarized light, re-enters the nitrobenzene cell, as it propagates from right to left. Now within the nitrobenzene cell, there is again a phase shift of pi by 2. For example, if the EY field gained a phase of pi by 2 with respect to the EX field when going from left to right, then when going from right to left, that EY field gains a further phase of pi by 2 with respect to the EX field. So what comes out of the nitrobenzene cell as the radiation propagates now from right to left is radiation which is polarized perpendicular to the incident direction of polarization. The initial direction of polarization was assumed to be vertical, and so when the radiation passes through the nitrobenzene cell for a second time, the first time it proceeded from left to right, and then it got reflected from the right hand mirror, proceeded from right to left, and so it passed a second time through the nitrobenzene cell, and when it has passed through second time, its direction of polarization has become perpendicular to the original direction of polarization, so it is now horizontal. So now this horizontally polarized radiation cannot pass through the polarizer, because the path axis of the polarizer is perpendicular to the horizontal direction, that is vertical. So the vertical path axis will not allow electric fields of polarization which is horizontal, and it is stopped, and so the radiation cannot re-enter the lasing medium, and therefore it cannot cause stimulated emission. So as it cannot cause stimulated emission, the population keeps increasing in the metastable state, and the population difference N2 minus N1 grows and grows and grows. So long as the flash is taking place over a period of say 2 milliseconds or whatever, 1 millisecond, this population grows and grows. Then when the flash is coming to an end, you suddenly also switch off the electric field. That is, you make V equal to 0. So there is no electric field between the two plates of the car cell. So as the electric field goes to 0, the birefringent property of the car cell also vanishes, and now the radiation that passes from left to right in the vertically polarized state returns to the polarizer in a vertically polarized state, pass through the polarizer, enter the lasing medium, and cause a huge avalanche of de-excitations. Therefore, suddenly the density of electromagnetic radiation increases within the lasing medium, and you have this Q switching. So long as the electric field was present in the right magnitude, and so long as the length of the car cell is of the right value, it was not possible for uh, stimulated radiation to cause to appear in large quantity. But the moment you uh, took away the birefringent property of the Kerr cell, this huge stimulating action takes place and a huge amount of stimulated radiation comes out, and then a huge burst of radiation can come out through the output mirror and proceed to the right. So this is how the Kerr cell acts. So it acts as a quarter wave plate, and because the radiation passes twice through it, it essentially acts as a half wave plate. And then this blocking action of the polarizer ensures that the stimulated emission does not appear until the flash is over and the electric field is removed and the system is ready to deliver a huge pulse. So in a typewritten note that I have sent you, a note on the Kerr cell, yes, I have given you this expression. The path difference between the two components, one parallel to the electric field and one perpendicular to the electric field, is equal to mu parallel minus mu perpendicular into L. And for the Kerr cell, this quantity is proportional to the square of the electric field and the length of the cell in the direction of propagation, that is the Z direction. So you can see that what gets electric field, the phase difference is given 2y by lambda capital D, and you can see how to get a phase difference of phi 2, what length to take, what is typical value of E. So because the coefficient P K is very small, because Ck is very small, you have to pay the large value, and the fact that E occurs in the second power as E square helps that. But nevertheless, because of the very small value of, you have to apply a very large voltage across the two plates. This very large voltage in the range of 10 to 20 kilovolts, which is pretty dangerous. You have to take all kinds of precautions and put in insulators around the Kerr cell and so on, so that the person who is using this device does not get a electric shock, which can be fatal because the voltage difference is 20 kilovolts or something like that. So that is one of the problems with the Kerr cell. You have to have a huge this potential difference between the two planes. So it is here that the focal cell is better and safer. So if you can go back to the text, we can now discuss the focal cell. Yeah, just take it away. Right. Here. This is the focal cell. Okay. In the focal cell, yes. So you use the Focal's effect. Focal's effect is like this: that certain materials like potassium dihydrogen phosphate, it's a crystalline material, develops this birefringent property or double refracting property under the action of the electric field. So this is known as Focal's effect, and the property is made use of in this focal cell type electro-optic shutter. Again, you can see the diagram
इसमें नया
here.
लड़का आ रहा है.
One is the that the lasing material, that is the ruby rod, is
ठीक है,
has
हम
a
खाली कर देंगे अगर कुछ होगा.
mirror to the left, which is
पीछे
100%
खाली है,
reflecting
उसमें कुछ
mirror,
है नहीं.
and there is the polarizer, which produces a uh, uh, which produces linearly polarized
अगर आपको साफ
electric
करना हो तो
field.
कर सकते हो खाली.
So this linearly polarized electric field, it proceeding to the light, which is linearly polarized by this uh, polarizer, enters the focal cell. Now, there are two types of focal cells. One is a longitudinal focal cell, and the other one is a transverse focal cell. The description given in the book by Lord apparently refers to a longitudinal focal cell. So in the uh, handwritten diagrams that I have sent you of focal cell and transverse cell, I have shown you this. If you can show the hand-drawn diagram once again. Yes, I have shown a longitudinal focal cell. The electric field is applied along the axis of the cell. So, this is the arrangement. In the transverse focal cell, the electric field is applied perpendicular to the axis of the cell, as in the car cell. The transverse cell is like the car cell, and operation can be understood easily by referring to the operation of the car cell. But apparently in Lord's book, they are referring to a longitudinal focal cell. So I will just tell you why. You can just, that is the essential thing, right? You can see the polarizer followed by the longitudinal focal cell, which contains the potassium hydrogen phosphate crystals, and then to the right you have an analyzer, and then the right hand mirror, which is 95% reflecting or something. So we can go back to the textbook now. Yeah. So we go back to the textbook, and yeah. So now what happens is that the radiation after passing the focal cell is now again linearly polarized, but the direction of polarization is perpendicular to the direction in which it was polarized falling on the focal cell. Initially, if the polarization was vertical, then after passing through the focal cell, the polarization becomes horizontal. This I have shown in the hand-drawn diagram, but you refer to it later. So this wave plate, the curved cell is so made that it acts as a quarter wave plate, but in the radiation half wave plate. But the focal cell itself, such a size, electric field is such that it acts as a half wave plate. As the radiation passes, its plane of rotates by 90 degrees. So when it falls on the polarizer, whose path axis is oriented parallel to the path axis of the polarizer, it prevents radiation from propagating towards the right hand mirror, because the direction of polarization of the radiation after coming out from the focal cell is horizontal, whereas the path axis of the analyzer is vertical. So it stops the radiation proceeding towards the right hand mirror. Unless it proceeds to the right hand mirror, it cannot get reflected, and therefore no radiation gets reflected back towards the lasing medium or ruby rod, and therefore stimulated emission cannot take place. So the population grows by virtue of the excitation produced by the xenon lamp, and N2 minus N1 grows and grows and becomes large, and then when the flash is just going to end, remove the electric field applied across the focal cell, so its birefringent property vanishes, and then any radiation that passes through the focal cell does change of direction of polarization, so it can pass through the analyzer, get reflected by the right hand mirror, return to the lasing medium, and in this way, huge amount of stimulation takes place within the lasing medium, and a sudden burst of uh, de-excitation and a huge flash of light now can proceed through the right hand mirror and come out as a huge pulse of radiation. So the radiation appears at the end of the period during which the excitation was being produced by the xenon flash lamp, and the entire delivered in a single pulse of duration a few hundred nanoseconds. So it can be a very powerful pulse that can cause photo uh, chemical reactions. It can be used to create an explosion, and it can be used in various different ways. The advantage of the focal cell is that the electric field needed is relatively small, and only 1 to 5 kilovolts is enough to produce the required action. So it is much safer to use. That is why this focal cell type electro-optic shutters have almost entirely replaced the Parse cell type electro-optic shutters. In the next page, let's move to the next page. In the next page, they have given some, move forward slide, yes. Here they have given some sample formulae, which tell you how to find the phase difference between the two waves, the component polarized along the x-axis and the component polarized along the y-axis. By the way, the direction of the electric field defines the optic axis, which I am referring to as the x-axis. So you can see that the two waves are propagating with different speeds because the refractive indices are different, and you can calculate the phase difference. And you require the phase difference to be equal to pi, okay, so that the electric vector of the incident radiation rotates by pi by 2. If the phase difference between the component whose polarization is along the x-axis and the component whose polarization is along the y-axis differ by pi, then the overall electric vector rotates by an angle pi by 2. That is what is achieved in the focal cell, whereas the Kerr cell is so designed that the rotation of one component, so the y component, the phase gain of the y component with respect to the x component is only pi by 2. So the net effect is that the linearly polarized light which is incident on the Kerr cell is turned into a circularly polarized light as it comes out of the Kerr cell. And again, when a circularly polarized light falls on the Kerr cell, it is coming out as a linearly polarized light. That is how Kerr cell acts. We can now move to the next page. Let's move on. Yeah. So here. Okay. So we are already on to 10:12. I want to finish by 10:15. Okay. So let's quickly go through this. Here we are doing some very elementary calculations of peak power emitted during the pulse. So N0 is equal to the total population per unit volume. So as you know, N0 is equal to N1 plus N2 because N3 is negligibly small. We have a 3-level system, so 1, 2, 3. The third level is very thinly populated. You can ignore the population. So basically, it's the sum of the populations of the ground state, that is N1, and the metastable state, which is N2, is equal to N0. They have defined normalized populations, writing them as small n2 and small n1. The sum of this has to be equal to 1, and then the single pass gain of the rod is given by this. Now here, when they write this expression, they are ignoring uh, the uh, losses, because remember that it is what they are writing is the gain within the rod. The mirrors are not in the picture. Because the mirrors are not in the picture, the uh, loss due to imperfect reflection is not taken into account in writing this formula. So it is, the gain is, as we know, exponential of alpha into L. Now what is alpha? Alpha is sigma 0 into n2 minus n1. This should be multiplied by capital N0. So what is written here is not correct. It should be sigma 0 into small n2 minus n1 into capital N0 into L. So you can just correct that formula. It should be sigma 0 into small n2 minus small n1 into capital N0 into L. As you can easily check by going back to the Ladenburg formula. If you go to the Ladenburg formula, you will see that that is the case. So this is the gain. Okay. Now, suppose, as they say, that the initial population inversion, because this difference n2 minus n1 is referred to as the normalized population inversion. So suppose the normalized population inversion before this one is Ni, and after the end of the pulse it is Nf. Now this is again a wrongly written statement. The population inversion before the shutter, not what he means by shutter is switched on, is actually he means that the electric field is removed. It is at the instant that the electric field is removed, not the instant when the electric field is applied. So when he says switched off, actually it should be it should not be switched on, it should be switched off. When the shutter is switched off, the electric field is removed, then it is Ni, and when the pulse is delivered, it is Nf. Initially, the population inversion is large, but when the electric field is removed, a giant pulse is produced because the excited atoms de-excite to the ground state. So the population inversion becomes small. So Ni is large, Nf is small. Ni is large at the moment when the electric field is switched off, not on. And later when the pulse is delivered, it goes to Nf. So how much energy is delivered? It is half Ni minus Nf N0 V H cut omega. H cut omega is the energy of each photon. How many photons are delivered? It is equal to the number of transitions. How many transitions? Because in each transition, the population difference changes by half into, in each transition, the value of small n changes by 2 units. Suppose the initial values of small n2 and small n1 are say 200 and 0. Let's say initially small n2 is 200. Sorry, small n2 is into n0. Small n2 into n0, that is capital N2, is 200, and small n1 into n0, that is capital N1, is 0, let's say. Then that is not the case. As we know, the ground state cannot be completely depopulated. But anyway, suppose capital N2 is 100 or 200 and capital N1 is 0. So when a transition takes place, capital N2 becomes equal to 199 and capital N1 becomes equal to 1. So the difference has now become 198. Initially it was 200, now it is 198. That means in each transition the difference changes by 2 units. So when the population difference goes from Ni into capital N0 to Nf into capital N0. The number of transition that has actually taken place is half of that. That is half of Ni minus Nf into capital N0. So many transitions have taken place per unit volume. So if the volume of the lasing medium is capital V, you multiply that by V, that is the total number of transitions within the lasing medium, and then in each transition a photon of energy h cut omega is produced. The total energy delivered is equal to half Ni minus Nf into N0 V h cut omega. Okay, let's move to the lower portion. Move to equation 11.8. Here they are saying that the in one back and forth motion, the time taken is equal to 2L by C. Once again, that C should be replaced by V, because the lasing medium has a refractive index, so it should be V. 2L by V is the time taken for one back and forth motion, and then in one back and forth motion, the radiation gets reflected once by the perfectly reflecting mirror and one by the imperfectly reflecting mirror with reflectivity R. Therefore, after one round, the amount of energy that is lost or radiated away is 1 minus R of its initial energy. So the question is, how much time would it take to lose all the energy? That's the question. Now, in one back and forth motion, the time taken is T1, so the energy lost in one back and forth motion is 1 minus R into T1. So, the mean life of the time over which radiation takes place is inverse of that. That is T1 by 1 minus R. So in one back and forth motion, energy lost is 1 minus R. This is lost in time T1. So the amount of energy lost per second is 1 minus R by T1. And therefore the total energy is lost in a time which is inverse of that. That is T1 by 1 minus R. So this is a very approximate formula. You can say that the mean life is something like T1 by 1 minus R. So if it is the mean life, then the total duration of the pulse may be assumed to be twice that, as they say in the next page. As they say at the bottom here, they say that the total span of the pulse is 2 Tc. That is, the pulse is delivered in a time equal to 2 Tc. That is twice T1 by 1 minus R. So if the duration of the pulse is twice Tc, what is the delivered power? That is given in the next page. That is Pm equal to E by twice Tc, where E is equal to half of Ni minus Nf into capital N0 into V into h cut omega. So that is an estimate of the power delivered during the occurrence of the pulse. Okay, and so suppose Tc is, I think I should quickly finish. Suppose Tc is, let's say, 1 nanosecond. Let's say Tc is 1 nanosecond, and let us, if Tc is 1 nanosecond, then what is the length of the lasing rod? The time, sorry, not Tc. Okay, so how much? Suppose T1 is 1 nanosecond and R is equal to 0.95. So what is Tc? 1 nanosecond into 1 nanosecond into, that would the 20, I think. Yeah, 20. So 20 nanoseconds. PC would be 20 nanoseconds. Well, it's something like 50 or 100 nanoseconds. And the total amount of energy delivered, let's move slightly upwards. Suppose the total amount of energy delivered is equal to, say, 10 joules. So what is the delivered peak power of the pulse that is produced? It is uh, equal to something like 10 joules by, say, 100 nanoseconds. So that means 100 nanoseconds means 0.1 microsecond. So 10 joules by 0.1 microsecond, that means 10 to the power 8 megawatt, 10 to the power 8 watts, that is 100 megawatts. So that is the kind of power that is delivered during the time of occurrence of the giant pulse. I have assumed E equal to 10 joules and twice PC equal to 100 nanoseconds. So that will give you 10 to the power 8 watts or 100 megawatts. That is something that is typical of this Q-switched lasers. It can deliver light powers of the order of 100 megawatt. That can be as large as that. So with that, we have to what this. So with that, we will be able to basically conclude this course. Okay. So thank you very much.
Thank you, sir.
Thank you, sir.
Okay. We next meet on next Thursday, hopefully, or next Friday.